The last lesson for this chapter is day 5, continuity. So if we look at this graph, what points do you think are continuous? So the continuous points would be at B, it's continuous. At D, it's continuous. At E, right over here, it's continuous. And at H, because it keeps going over to the right. So those are continuous, highlighted in green, and then discontinuous, I'm going to say C. F, it's discontinuous. G, it's not continuous. And at A, it's technically not continuous because it stops, it doesn't keep going, so we'll say A too. Okay, so our definition of continuity, the function at the value that we're talking about, the continuity at a point, at whatever value that is, has to exist. Number 2, the limit has to exist. And number 3, the limit must also equal the function value. And this shows continuity at a certain point on the interior of the function. For the whole function to be continuous, it's got to be continuous at every point in its domain. Okay, so we have a few different types of discontinuities, and we've talked about these before. This one right here would be a jump. Kind of jumps from there to there. This is an infinite. The next one. Limit as x approaches a of f of x equals infinity. Just to refresh your memories from last class. This is also an infinite discontinuity. Any of those vertical asymptotes are infinite discontinuities. Now this one, if we're saying the limit as x approaches a, we'll say the function's named f of x. This would be a does not exist because it goes up to infinity down to negative infinity. Remember, if it equals infinity, technically that's also does not exist because you're not actually reaching a value. It's just kind of the idea of infinity. And this last one is also infinite. But we could say that the limit as x approaches a of f of x equals negative infinity. Okay, down here, these two at the bottom, they're both removable. Or point discontinuities. So you could have just a hole in the graph like this one, or you could have a hole in the graph with a function value somewhere like this one. They're both removable or point. Okay, so we could make a function continuous, so removable discontinuities come from rational functions. A piecewise function can be used to fill the hole. So let's say you have a function that's rational, so it's a fraction. There, if you factor, so if we look at this, g of x equals, it's going to be x plus 2 times x minus 2 over x minus 2 when x doesn't equal 2. That's this right here. So those x minus 2's cancel out. That gives you a hole. But they're filling it in with this value of k right here. So I'm going to say g of x is this top function right here simplifies to x plus 2 when x doesn't equal 2, and it equals k when x equals 2. Okay, so how do we make that continuous? We want x plus 2 and k to be equivalent when x equals 2. So our limit as x approaches 2 of g of x equals 2 plus 2. Remember, it was x plus 2. So that equals 4. So that y value of 4 is where it's going to approach, but it had that hole there. So you're going to set k equal to 4. So essentially we're setting x plus 2 equal to 5. Equal to k. I don't know why I just said 5. Okay. Next one, show whether the function is continuous or not at x equals 1. So x equals 1 is kind of like this cutoff point right here. So I'm going to write my limit as x approaches 1 from the left of g of x, and it is the top function there. So it's 1 minus 1 squared, which equals 0. Then I'm going to do my limit as x approaches 1 from the right of g of x, which is 1 over 1.
How can you do that? How can you do that, Mommy?
I'm just writing on here.
How can you do that? Wait, Mommy, what are you doing?
I'm just, I'm doing a lesson on the iPad. You could say hi, James. Some of my students might listen to it. You want to say hello?
Yeah.
Say hello.
Hi.
All right. Good night. Love you.
Good night.
So they equal different values when you're coming from the left and the right of the function. So you're going to say g of x is not continuous. Because the limit as x approaches 1 from the left of g of x does not equal the limit as x approaches 1 from the right of g of x. Okay, the next example is asking us to redefine the function so that it is continuous. So if we simplify this function, f of x equals x times x plus 3 over x plus 3. So that simplifies. We have a hole here, or removable, or point discontinuity, at x equals -3. So in this function, x can't equal -3. Makes the function undefined anyway. So we have f of x equals x. So f of -3, if I plug in -3 into this function, is going to equal -3. That's that y value that would have a hole there. The hole would be -3 comma -3. So what I want to do is write the original function, x squared plus 3x over x plus 3. And that's for all values such that x doesn't equal -3. And then I'm going to fill in that hole. I'm going to say, okay, well, it's going to equal -3 when x equals -3. So what this function is doing is, this is the line f of x equals x, or y equals x. And it had a hole over here. Oh, I'm going to erase the whole thing. It had a hole over here at -3. And then this right here fills in the hole. So we have a continuous function. So we redefined it, so now it's continuous. Okay. This next one, now we have to find the value that's going to make f of x continuous. So let's do our limit. We got to go limit from the left. So as x approaches 3 from the left of f of x equals, that's a little bit less than, so it's going to be 3 squared minus 1, which is 8. And then we're going to do our limit as x approaches 3 from the right, from the right of f of x, which will be that one. So it's going to be 2a times 3 when x is equal to 3. So that's going to be 6a. And now what we want to do is these two, the left and right hand limits, we want to be equal. So we're just going to say, okay, a equals 6, or 8 equals 6a. Divide by 6, and a, when we reduce it, is 4/3. Okay, so example 4 is the same type of deal. Limit as x approaches 1 from the left of f of x is that right there. And that's 7 times 1 minus 2, which is 5. Limit as x approaches 1 from the right of f of x is k times 1 squared. So that's just k. And we're going to set these equal to each other. This one's nice and easy. K is just going to equal 5. That's our solution. Okay, letter B. Limit as x approaches 2 from the left of f of x is going to be k times 2 squared, which is 4k. Limit as x approaches 2 from the right of f of x equals 2 times 2 plus k. That's this one right here, which is 4 plus k. Set them equal to each other. 4k equals 4 plus k. 3k equals 4, so k equals 4/3. Okay, so what values of a and b make h continuous? All right, so we got a system of equations. We have to solve for two variables here. So I am going to check the limit as x approaches 2 from the left. Or no, not 2, negative 2. Limit as x approaches negative 2 from the left and right. So we got kind of like this cutoff point right here. And then I'm going to do the limit as x approaches 1 of h of x from the left and right. So like that cutoff point right there. So our limit as x approaches negative 2 from the left of h of x is just 3. Our limit as x approaches negative 2 from the right of h of x equals a times negative 2 plus b. So it's going to be negative 2a plus b. All right, now I'm going to do, actually, before I do that, I want 3 to equal negative 2a plus b. All right, I can't solve yet. I have two unknown variables, so let's try to get another equation using the 1. Limit as x approaches 1 from the left of h of x equals a times 1, so a plus b. Limit as x approaches 1 from the right of h of x just equals negative 3. So my next equation, a plus b equals negative 3. Okay, so now that we have that, you can either use substitution or use elimination, whichever method you like best. So I'm going to take both of these equations. I'm going to say, all right, negative 2a plus b equals 3. A plus b equals 3. All right, I'm going to subtract the bottom equation. That way the b's will eliminate. So I'm going to have negative 3a, b's cancel out, equals, was a negative 3 here, so that'll be 6. A equals negative 2. Got my value of a, just go back into either one of the originals. a plus b equals -3 was one of my original equations, so -2 plus b equals -3, and b equals -1. Okay, last page. What three things are needed to be true in order for a function to be continuous? This was on the first page of the notes. We have f of c must exist. So whatever that value is, we can't have a hole or anything in there. Limit as x approaches c of f of x must exist. So remember, in order for the function to exist, the limit as x approaches c from the left of f of x has to equal the limit as x approaches c from the right of f of x. And our limit as x approaches c of f of x has to equal that function value, f of c. Okay, for number 4, find the value for a that will make the function continuous. All right, so let's do our limit as x approaches 1 from the left of f of x is 1 squared plus 4, so 5. Our limit as x approaches 1 from the right of f of x equals a times 1, so a plus 2. So a plus 2, set these equal to each other, equals 5, and a equals 3. Okay, number 2, is the piecewise function continuous at x equals 0? Explain using the rules of continuity. Okay, so what you're going to do, notation is very important, so I'm going to write it out correctly. Limit as x approaches 0 from the left of f of x equals 4 times 0 plus 2, which is 2. Limit as x approaches 0 from the right of f of x equals 0 squared minus 2, so -2. So the answer is going to be no, because our limit as x approaches 0 from the left of f of x does not equal our limit as x approaches 0 from the right of f of x, which means our limit doesn't exist, which means that we don't have a continuous function. But writing this is sufficient for that. All right, is the piecewise function continuous at x equals 2? All right, so same type of question, although I believe this one turns out to be continuous. So limit as x approaches 2 from the left of f of x equals 2 squared plus 1, so 5. Limit as x approaches 2 from the right of f of x equals 3 times 2 minus 1, so 5 as well. And this is going to be yes, because our limit as x approaches 2 from the left of f of x equals our limit as x approaches 2 from the right of f of x. That tells us our limit exists. Then we also have to state that it equals our function value at 2. That shows us there's no hole in there. So that's your complete explanation for that. You want to write all 3 of those things, very important. Okay, last one, a little system of equations here. We're going to check from the left and right at 2, then we're going to check from the left and right at 1, and we'll set up our system. So limit as x approaches 2 from the left of f of x equals, oh, this is -2, not 2. Okay, 3 times -2 minus a, so -6 plus a. Limit as x approaches 2 from the right of f of x equals 2, again, -2, times -2 squared plus b, so that's going to be 8 plus b. Okay, so our first equation right here gives us -6 plus a equals 8 plus b. Okay, then we have our limit as x approaches 1 from the left of f of x equals 2 times 1 squared plus b, so it's going to be 2 plus b. Then we have our limit as x approaches 1 from the right of f of x equals 5 times 1 minus 1, which is 4. So these equations right here, I'll do this over to the left, gives me 2 plus b equals 4. That's really nice because we only have one variable. I know from there b equals 2. So now I can go back up to this equation and I can say, all right, well, negative 6 it should be a minus a, not plus a. Fix that. Negative 6 minus a equals 8 plus 2. Negative 6 minus a equals 10. Negative 8 is 16. So a equals negative 16. Okay, so that's it for your first chapter of calculus in pre-calc. Good job.